Let's actually see this math working. To illustrate, I will rely on a study published in the Journal of Organizational Behavior, examining the effect of economic stress on entrepreneurs' beliefs about their future. The data collection is cross-sectional in nature and comes from a survey of over 200 small business owners in Virginia who responded to a questionnaire during the recession of 2008-2009. A set of 2 items in the questionnaire were used to quantify the entrepreneur's economic stress. You can see the question wordings here. The responses to these 2 questions using this response scale were averaged to produce this measure of economic stress felt, with higher values reflecting more economic stress. Also measured was their business-related depressed affect, tapping into the extent to which they felt various negative emotions about themselves vis-a-vis the operation of their business over the last year. So feelings such as discouraged and hopeless and so forth. Again, on this scale here, and responses were aggregated over items to produce a measure of business-related depressed affect, where of course higher is more depressed affect. The outcome variable, which will be Y in all the diagrams that you see using this example, is their entrepreneurial withdrawal intentions. This is a common dependent variable in the study of entrepreneurs and taps into the likelihood of a person's likelihood or willingness to continue pursuing entrepreneurial activities. You can see the items here, and again, their responses were aggregated to produce a single measurement of withdrawal intentions, where higher is greater intentions. And that's actually pretty consistent for all 3 measures, right? So higher values on economic stress reflect more economic stress felt. Higher values on business-related depressed affect reflect more negative affect, and higher values on withdrawal intentions reflecting higher withdrawal intentions. What we're going to do with these data is assess the possible effect of economic stress on intentions to withdraw from entrepreneurship. You can imagine how feeling stress about how your business is going to survive in bad economic times could lead you to feel that perhaps you should just throw in the towel and pursue some other kind of professional lifestyle that maybe is less risky, even if it means you lose some independence by having to have a boss of some kind. Okay, so these data are correlational in nature, right? It was just people's responses to a set of questions that they were asked during one sitting. But that doesn't preclude us from using regression and path analysis to estimate the effects of one variable on another that may be in causal in nature. And there's that word effect, the very loaded term implying cause-effect. I don't know whether the relationships here that I'm modeling are causal in nature. But I'm going to do a mediation analysis in the end, recognizing that whether these are truly causal relationships is not something that any statistical method will be able to tell me. Of course, you need to provide an argument when you are doing analyses of this sort. You would need to make the argument as to why you believe that the relationships that you are modeling are causal in nature. If you don't make that argument, expect some critics to take you to task, and they will either reject your paper or they will insist that you put together a stronger argument than you have as to why you're configuring the variables in a particular causal sequence. We'll get more into this debate and discussion later. This is the first time we've seen any data in this class, so I want to talk a little bit about the form the data files will take, depending on whether you're an SPSS SAS or R user for the purposes of this course. In the archive of course materials you're likely to have already downloaded from the course portal, you will find a set of folders containing the data used in various examples in this class. There's a folder for SPSS, one for SAS, and one for R. The SPSS version of the data files are already prepared for you, and they'll look something like this when you open the data by choosing File and Open in the SPSS menus. So this is an SPSS data file, and it's all ready to go for you. You don't have to do any other work to analyze this data. All you need to do is open it up. For SAS, I've not prepared SAS data files for you. Instead, I've given you SAS programs that you should execute to produce the data files. The resulting SAS data file will be, in the language of SAS, a temporary or work data file. If you want to turn these into permanent SAS data files, you can do so on your own time, but it's not necessary for the purposes of this course. So the SAS E-stress file would look like this, and you will simply execute this program to produce the E-stress data file. So these are what the two E-stress data files look like in SPSS and SAS. And the three variables we're focusing on here are the ones in the columns labeled E-stress, affect, and withdrawal. That's entrepreneurial economic stress, business-related depressed affect, and withdrawal intentions. You can see that the data are the same in both SAS and SPSS, although the format is different. This is in a nice spreadsheet. This is just a text file. So if you're using SPSS or SAS, you want to open up the data file in SPSS or load the E-stress program that creates the E-stress data file. And I trust you already know how to do that. For our users, I've provided the data to you in the form of comma delimited text files, or what's sometimes called CSV format. This is a format that R can easily read and that many people use to import data into R. If you were to go to the estress.csv file in the course materials and just double-click, your computer would probably open up Excel if you have it installed. But you can open the data file in any text reader and it would look something like this. And this, of course, is just an excerpt. The actual data file itself is much bigger. At the top, the so-called header are the variable names. And then everything that follows is the data with individual data points separated by commas. Each row represents an entrepreneur, and then the data points are in the sequence of the variable names in the header. You want to read the CSV file to produce a data frame. If you've been using R, you no doubt already know how to do this. And of course, you should be congratulated for this because R is quite difficult for many people to use, and one of the bigger challenges is just learning how to get data into R in the first place. But I'm assuming you're already at that point if you've chosen to use R for the purposes of this course. Now you want to make sure you put the R files, the R data files, in a location on your computer to which you can refer using standard folder path notation for your operating system. For example, in this code, I am telling R that my E-stress data frame that I'm creating will be created by reading this E-stress data file, which is located in this location on my computer. I'm also telling R that the data points are separated by commas and that there is a header that contains the variable names. If you'd rather not write the path for every file that you're reading throughout this course, if you want to just always put your data files in the same location, you could use the setwd command, which stands for set working directory, to change your working directory to wherever your data files are located. That way you won't have to list the data file location every time you're reading data. But this is also probably something you already knew. This head E-stress line will just print in the R console, or if you're using RStudio, it'll print somewhere in RStudio so that we can see how the data file looks. And it's a good idea to do that just to make sure that the data file is being read. So here is the result of executing this line, these two lines in R. We'll get something like this on the screen. And it looks like it found the data and it read it in correctly. Now I want to point out to you that there's a large R program in the course materials that contains, among other things, code to read the data files for this course. In that code, I have used the set working directory command. I'll show it to you here. So here I'm just telling it to set my working directory to this location and then read the data file and show me the first few lines of the data file. So when I execute this in R, there it is. So that's how you'll be creating and reading and creating data files in this course for you R users. I have a little bit more housekeeping to do before we actually do any kind of modeling with the E-stress data file. This section here is for SPSS users. If you're a SAS or R user and you're not interested in listening to this, you could just fast forward a few minutes to skip this material. Of course, we welcome you to listen in. Many people are drawn to SPSS because of its very easy to use graphical user interface, or GUI or GUI. This GUI allows you to conduct analyses and do other data analysis tasks using just your mouse and various menus available to you at the top of the SPSS program. Although this is convenient, this is not how we're going to be interacting with SPSS in this class. Instead, we're going to talk to SPSS by writing syntax or code. You may already have some experience doing this, but in case not, I want to provide a quick tutorial to those needing it. For more details on the use of syntax, including the many reasons why you ought to develop this skill, independent of your need to use syntax in this course, you can see my little syntax guide that's available in the materials I provided for this course. It can also be downloaded from my homepage at afhayes.com. So looking at the slide here on the screen, what we're going to do is we're going to open up a new window, a syntax window, and into that window we're going to be typing commands. We're going to type words into a blank window that opens up, and then we will run or execute those commands. But that's fairly abstract, so I want to actually demonstrate this to you. So I'm going to go to where I've got my data file open, and I'm going to go up to File and select New Syntax. My computer is a little bit slow today, but here it is. And this opens up this window in SPSS. Looks like a blank screen. That's pretty much all it is. The dreaded blank page that you might find when you are facing a new writing task using your word processor. It's in this screen here, and you can see a cursor typing up here, blinking up here, that we're going to type in our commands. Now this window here I find to largely just be a nuisance, and so I'm going to minimize that, but you don't have to if you don't want to. If you've got that window, I'm just going to move that over. Actually, I'm just going to make it go away entirely. Okay, so there is my syntax window. I'm going to make this a little bit smaller so I can see a bit more of what's on the screen. Okay, so we're going to type commands into SPSS to tell it what we want to do. So once you start typing, and I'm just choosing some random letters here, I just want to point out that you will eventually probably want to save what you've typed. And you can do that under File, Save, just like you would when using a word processor. If you have familiarity with a word processor, and no doubt you do, you will find that most of the usual word processor functions are available in terms of cutting and pasting and doing other things of that sort. I've also provided to you in the course materials a large program containing various code or syntax that we're going to be using throughout this course. So you can go hunt for that if you wanted to, and you do that by opening a syntax file. You don't need to do that now, but I wanted to make sure you were aware that that program is available. Okay, so anticipating the next slide, go ahead and type in the word correlations, variables equals e-stress withdraw, and then terminate that with a period. Make sure you type the period. This is very important because it tells SPSS that this is the end of the command. Just like when you're writing to tell the reader that your sentence is done and what follows is a new sentence. If you forget the period, SPSS will usually get quite confused because it won't know when one thought ends and another begins. This command is telling SPSS to calculate Pearson's coefficient of correlation between the economic stress variable and the withdraw variable. And when we execute this, it will operate on whatever is currently the active data file. We only have one data file open, so it's the active data file. You can always make a data file active by choosing it in the window or just clicking on it somewhere. Now, if you were using the graphical user interface, to calculate this correlation, you would have to be finding the correct menu, such as menu here, correlate, and so forth. But that's a lot of pointing and clicking. And when you get used to writing code, you'll find that writing code is much, much faster and it's much more efficient. And again, there are many other reasons why you should learn to write syntax. See the little syntax guide for some details on 11 reasons I give. Once you type in the command, you have to execute it. And there are a number of ways you can do this. One of them is to take the cursor, which you can see is blinking there, and just place it anywhere in the sentence that is the command. And then you can press this button, which looks like a play button on an old VCR or a DVD player. An alternative is you can go up to run and say run that selection. When I say selection, that's another option for you. You can also just click and drag across the code that you want to execute and then press the play button. That can be useful when you want to execute multiple commands at the same time. Choosing to place the cursor somewhere in the line will only execute that one line, which of course we only have one line right now. But when you have multiple lines, you can click and drag across all those lines and run them all simultaneously by clicking the play button or choosing run selection. If you wanted to run the entire program, again, ours currently has only one line, but if you wanted to run the whole program, you could also choose the run all option. Now I'm going to go ahead and execute this command. I'll just go ahead and highlight it, and then I'll click the play button. And it looks like it did nothing, but it actually did. Go under Window and in the output, and you'll see that it has created this table. We're going to talk about this a little bit more in the next slide. But here we see Pearson's coefficient of correlation. If you have an error, and you might, if so, you will probably find it here in the output window. That means you did something wrong. Sometimes the errors are very, very hard to make sense of, but very often they are the result of something simple, like you mistyping a command, or or using the wrong name for a variable, or maybe you've used a variable name that doesn't actually exist in the data file. I promise you, with practice, you will get used to this and your errors will become less frequent, although you will never completely avoid creation of errors by sloppy typing and other things. SPSS can be quite finicky when it comes to syntax. So for instance, it cares a lot about spelling. If we spelled e-stress wrong, which is a variable name in the data file, it would look for a variable name that's spelled the way we spelled it. And if we misspelled it and the variable doesn't exist in the data file, it's going to give us an error. It would also care if we misspelled words like variables and other things. Other things it doesn't care so much about. For instance, it doesn't care about case. I could put this all in caps and it wouldn't care, or I could have a mixture of lower and uppercase. It also wouldn't care about that. If you're an R user and you're listening in, remember that R is a case-sensitive language. So E-stress in lowercase is different than E-stress in uppercase. That's something you want to keep in mind. But if you're an R user, you probably are already aware of the case sensitivity of commands and variables in R. Okay, so we're going to do a couple more examples of commands in SPSS in the next few lines, but I wanted to make sure that SPSS users always have, SPSS users have some experience in practicing working with syntax before we get more heavily into some of the modeling that we're doing. Linear regression analysis is the foundation of this course. We will be using OLS regression extensively to estimate various effects, whether mediated, moderated, or both. The foundation of linear regression analysis is Pearson's coefficient of correlation. Almost all computations conducted by a linear regression analysis routine involve correlation between variables as well as means and variances. I'm assuming you're already familiar with Pearson's coefficient of correlation, which is frequently denoted with a small letter r. It's a measure of linear association between two variables that can range between -1 and 1. The sign indicates the direction of the association, and the distance from 0 reflects the strength of the association, or how accurately you can estimate one variable from knowledge of the values of the other variable. Let's look at the correlation between economic stress felt by the entrepreneurs in this study and their intentions to withdraw from entrepreneurial activities in the future. All statistics programs worth anything will generate Pearson's R between two variables. In these three boxes here, I provide code for SPSS, SAS, and R to generate the correlation between economic stress and intentions to withdraw from entrepreneurship. I generated this output using SPSS in the last slide. The convention that I will be using is to place SPSS code in a black box with white text, SAS code in a white box with black text, and R code in a gray box with black text. You can type this code into your program and execute it to produce Pearson's R in the output window, where you can find this line of code in the programs I've provided to you, and you can execute it from there. As you can see from this SPSS output, the correlation is positive, but quite small by most people's standards. The positive association reflects the tendency for entrepreneurs who are feeling relatively more stress to report stronger or greater intentions to withdraw from entrepreneurship in the future. You may notice that this relationship is not statistically significant, but remember what I said earlier, lack of correlation does not disprove causation. We'll talk about inference a little bit later on. Let's visually depict this association using a scatter plot. A visualization tool you no doubt have seen and used before. Here's the code in SPSS, SAS, and R that will generate a scatter plot of the relationship between economic stress and entrepreneurial withdrawal intentions. These commands are formatted so that economic stress will be on the horizontal axis and withdrawal intentions on the vertical axis. For SPSS users, I'll go ahead and demonstrate the execution of this command to continue to reinforce how to talk to SPSS using syntax. So here is the correlations command that I executed earlier. I'm just going to go ahead and type in a command to generate a scatter plot. I'll execute it by clicking on the cursor, placing it in the line, and then clicking the play button. There's the correlation that we calculated earlier, and here comes the scatter plot. You'll notice that it looks a little bit different than the one I showed you on the slide. I had edited this output, removing some of these lines and making other small changes. You can do that on your own if you'd like to explore. Just double-click on an output, and that'll put it into edit mode, and that'll allow you to change all kinds of things. This scatter plot, which you can see here, reflects the rather weak association revealed by Pearson's R. There doesn't appear to be much of a pattern here, but if you look carefully, maybe squint a bit, you might see some evidence of the positive association as the entrepreneurs lower in economic stress seem to also be lower in withdrawal intentions, and those higher in stress appear to be the ones more likely to be higher in withdrawal intentions. But if you can't see that, I don't doubt it at all. It is kind of hard to see. And this is a very subjective process, isn't it? I mean, after all, trying to find a pattern in what looks like a mostly random scattering of dots is certainly going to lead to disagreements. Now, imagine that you were to draw a line through this scatter plot that seems to visually depict the association. Your task is to connect the dots, but the line you draw can't curve or be jagged. You're just going to get one straight pass through the scatter plot, trying to get as close to all of the dots as you can with this constraint that it must be a straight line. Where would you draw it? Would you draw it here? Or maybe here? Or perhaps something more like this? Clearly, there's subjectivity to this. Where you draw that line might be different than where someone else draws it. Finding this best line is the essence of regression analysis. A regression analysis routine will find the mathematical formula corresponding to this line that best fits the data, where we define best fit using the ordinary least squares criterion, meaning that it minimizes the sum of the squared vertical discrepancies between the points in the scatter plot and the line. There's only one formula for a line that minimizes this residual sum of squares, that is, makes it as small as it can get. Let's now run a regression analysis to produce this equation for the line. We're going to estimate withdrawal intentions from economic stress, because in the study the example is based on, the authors were proposing that economic stress could lead people to ponder abandoning their entrepreneurial activity. So economic stress is thought to be the cause of withdrawal intentions. Traditionally, the variable representing the effect is put on the left side of the equation, and the proposed causes go on the right. So we're going to regress withdrawal intentions, that's our y variable, on economic stress, which we're calling x. Here are the commands in SPSS, SAS, and R that will conduct the regression analysis. I will demonstrate this in SPSS. Here are the 2 lines of code that we wrote earlier. Now I'm just going to regress, choose my outcome variable, and then my variables on the right-hand side of the equation. And then I execute this. And here's my regression output. We're going to focus on this section on the slide because that's where our best fitting model is provided. The best fitting OLS regression model is 2.062 plus 0.056x. The regression constant is here, and the regression weight for x is here. You should recognize this as the total effect of x on y, the total effect of economic stress on withdrawal intentions from our discussion of mediation analysis earlier. I'm going to talk a bit more about inference later, but for those of you who can't help but look, you might notice this total effect is not statistically significant, but we shouldn't let this discourage us from doing a mediation analysis, which we're going to do soon using these data. Let's take a closer look. Here is our regression model, and I've superimposed the regression equation onto this scatter plot. The line here is the outputs from this regression equation. We plug in a value of x, economic stress, into this equation, and out pops an estimate of an entrepreneur's withdrawal intentions, this y hat. Do this many times with different values of x, and then plot the result, and you'll get this line. This is the line that minimizes the residual sum of squares, the sum of the square discrepancies between the actual values of intentions in the data and the estimated values from the model. The slope of this line is 0.056. This is our total effect of economic stress on withdrawal intentions. So we can say that 2 entrepreneurs who differ by 1 unit in their economic stress, that 1 unit being a point on the economic stress measurement scale, are estimated to differ by 0.056 units in their intentions to withdraw from entrepreneurship. That's 0.056 units on the measurement scale, with the more stressed out entrepreneur expressing higher intentions to withdraw because the sign of the total effect is positive. This is our unstandardized or raw total effect of x on y. What about the completely standardized total effect of x? Recall that we could calculate that by standardizing y and x prior to the estimation of the model. The completely standardized total effect would then be the weight for standardized x in this model. But most regression programs can generate this without actually requiring you to do the standardization first. The completely standardized total effect of economic stress on withdrawal intentions is just the standardized regression weight from the model we generated earlier. SPSS will produce this automatically. In SAS and R, you have to ask for it. In SAS, you use the STB option here, and in R, use the scale operator. Here is our completely standardized total effect in the SPSS output under the column that says standardized coefficients. Our standardized total effect is 0.064. Remember that we interpret this as the estimated difference in standard deviations of y between 2 cases that differ by 1 standard deviation on x. Here's the completely standardized total effect in visual form. On the horizontal and vertical axes of the scatter plot, I've placed standardized economic stress and standardized withdrawal intentions. The standardized total effect of economic stress is the slope of this line. The slope of this line is our 0.064. We can say that 2 entrepreneurs who differ by 1 standard deviation in their economic stress are estimated to differ by 0.064 standard deviations in their withdrawal intentions, with the more stressed entrepreneur reporting greater intentions to withdraw from entrepreneurship. This is also just a Pearson correlation between x and y. Let's now bring a mediator into this problem. The authors of this study were interested in the mechanism by which economic stress might enhance the likelihood an entrepreneur will choose to close up shop, so to speak. They proposed an affective mechanism, whereby relatively more stress would lead to feelings of more despondency or depression about the prospects of success in one's business in harder economic times. And this would lead in turn to entrepreneurs entertaining more the idea of abandoning their business. So the model looks like this, with an indirect and a direct effect of economic stress on withdrawal intentions through business-related depressed affect. We want to estimate both the direct and indirect effects because stress could influence withdrawal intentions by some other means, that is, not through business-related depressed affect. If so, the direct effect should pick that up, although there are other interpretations of the direct effect. Let me point out as well, just to remind you that even though we found no significant relationship between economic stress and withdrawal intentions, that doesn't preclude us from doing a mediation analysis. It used to back in the 1980s, 1990s, even into the years of 2000, people wouldn't bother with mediation analysis without evidence of a total effect. But that's very much 20th century thinking. 21st century mediation analysis doesn't require evidence of a total effect before we entertain questions about the process by which an effect can operate. All right, so remember we already went through the estimation of the total effect of economic stress on withdrawal intentions. That was our total effect of X on Y. That's path C in our mediation model. Recall from our equations for the simple mediation model that we need to estimate the effect of X on the mediator, that's the A path, the effect of the mediator on the outcome Y controlling for X, that's the B path, and the effect of X on Y controlling for M, that's the direct effect of X, or the C prime path. So let's do that now using regression analysis. And once we've done so, you'll see that, as I promised, the total effect of economic stress breaks nicely into our two pathways of influence, one indirect through business-related depressed affect and one direct. To estimate the A path, we'll regress business-related depressed affect, our mediator, on economic stress, or X, or proposed causal agent. Here are the SPSS, SAS, and R commands that will produce both the unstandardized and the completely standardized A paths. I trust by now that for SPSS users, after my earlier demonstrations, you're probably familiar enough with typing and executing SPSS syntax that you don't need me to now show you how to run this line of code. Here's the output. This is SPSS output. Our unstandardized model has a constant and a weight for X here, so it's 0.799 plus 0.173X. That's our A path. Our completely standardized A path is the standardized coefficient, 0.340, so our standardized model looks like this. We're not going to talk about inference yet, but to forecast our eventual discussion, notice that this relationship is statistically significant. But that's not important because what we care about is the indirect effect. The A path is not the indirect effect. It's only a component of it. So whether or not the A path is statistically significant or not is not important for the inference about the indirect effect. Here are the generic interpretations of our unstandardized and our standardized effect of economic stress on business-related depressed affect. I've gone over these interpretations quite a bit already. You can read these on your own. They are consistent with the language that I've used earlier. We're going to focus instead on the substantive interpretations, which we will find in the next slide. Here is a visual representation of the effect of economic stress on business-related depressed affect in the form of a scatter plot, with the A path represented visually here on the scatter plot. As you can see, the relationship is positive. The slope of this line, this is the regression line, is 0.173. So we can say that two entrepreneurs who differ by 1 unit in their economic stress are estimated to differ by 0.173 units in their business-related depressed affect, with the more stressed entrepreneur feeling more depressed affect. The completely standardized A path is over here on the right. On the horizontal and vertical axes, I've placed standardized economic stress and standardized depressed affect. The completely standardized A path is the slope of this line, 0.340. The interpretation, Two entrepreneurs who differ by 1 standard deviation in their economic stress are estimated to differ by 0.340 standard deviations in their business-related depressed affect, with the more distressed entrepreneur feeling more depressed affect. Let's now estimate the B path, which is the effect of business-related depressed affect, that's our mediator, on withdrawal intentions, controlling for economic stress. To do so using OLS regression, we're going to estimate withdrawal intentions from both depressed affect and economic stress simultaneously. Here's the SPSS, SAS, and R code that does it. Our regression program, as we can see from the SPSS output here, tells us that the best fitting model is 1.447 minus 0.077x plus 0.769m. The B path in unstandardized form is 0.769. Or in completely standardized form, it's 0.446. Those numbers are here and here. This relationship is positive, and it's statistically significant, but again, that doesn't matter because our focus is going to be on the indirect effect for inference, and that's the product of A and B, not B itself. Here's the generic interpretation. These are consistent with the interpretations I've given in the past. Let's move instead to the substantive interpretation on the next slide. Here is a visual representation of the unstandardized and the standardized B paths, the effect of depressed affect on withdrawal intentions controlling for economic stress, in the form of what's called a partial scatter plot. This requires some explanation. Those of you who are really familiar with regression analysis principles will remember that regression coefficients in models like this, partial regression coefficients because it's from a multiple regression model, can be thought of as the result from regressing residuals on residuals. The values on the horizontal and vertical axes here are residuals from a regression analysis. Remember that we're estimating the effect of M on Y controlling for X. So we want to create two measures of M and Y that are independent of X. Now imagine regressing X on M and calculating the residuals from that regression analysis. Those residuals are on the horizontal axis here, and they're interpreted as how much more or less depressed affect an entrepreneur feels compared to how we would expect him or her to feel given his or her stress level. We know these residuals are uncorrelated with economic stress. Now imagine regressing Y on X and calculating the residuals from that model. Those residuals are on the vertical axis, and they represent how much higher or lower an entrepreneur's withdrawal intentions are, given what you'd expect that entrepreneur to be given his or her economic stress. These residuals are uncorrelated with economic stress as well. The B path is the regression weight for residual depressed affect when we predict residual withdrawal intentions from residual depressed affect. It's depicted here as the slope of this line. And here's how we interpret it. Two entrepreneurs who differ by 1 unit in their business-related depressed affect, but who are equal in their stress, are estimated to differ by 0.769 units in their withdrawal intentions, with the more depressed entrepreneur feeling greater intentions to withdraw from entrepreneurship. Using causal language, it seems that the depression gives rise to greater intentions to abandon one's business and start a new professional life. The completely standardized B path is here on the right. This partial scatter plot is generated in exactly the same way, except using standardized variables in the regression analyses used to construct the residuals. The completely standardized B path is 0.446. Two entrepreneurs who differ by 1 standard deviation in their business-related depressed affect, but are equal in their stress, are estimated to differ by 0.446 standard deviations in withdrawal intentions, with the more depressed entrepreneur feeling greater intentions to withdraw from entrepreneurship. Now let's look at the C prime path, the direct effect of economic stress on withdrawal intentions. That comes from the same regression model that we used to estimate the B path, so the output here is the same as we were looking at in the prior slide. The direct effect, C prime, in unstandardized form is 0.077, or the completely standardized direct effect is minus 0.088. The direct effect of economic stress is negative. Here's our generic interpretation, consistent with the interpretation I've given in the past. We're going to focus on the specific interpretation in the next slide. Here's a visual depiction of the unstandardized and the completely standardized direct effects of X on Y. These are partial scatter plots as well. They visualize the partial association between economic stress and withdrawal intentions controlling for depressed affect. These are also generated as plots of residuals against residuals. On the horizontal axis are residuals from estimating economic stress from depressed affect. These quantify how much more or less stress an entrepreneur is feeling, given how much stress you'd expect him or her to feel, given how depressed he or she is. These are linearly unrelated to depressed affect. On the vertical axis are residuals from estimating withdrawal intentions from business-related depressed affect, and they represent how much higher or lower a person's withdrawal intentions are relative to what you'd expect his or her intentions to be given how depressed he or she is. These residuals are also uncorrelated with business-related depressed affect. The direct effect, C prime, from the regression model we estimated earlier is equivalent to the weight for residual economic stress when you regress the withdrawal intention residuals on the economic stress residuals. That weight is minus 0.077, and it's the slope of this line. We can say that two entrepreneurs who differ by 1 unit in their economic stress, but who have the same business-related depressed affect, are estimated to differ by 0.077 units in their withdrawal intentions, with the more stressed entrepreneur feeling lower intentions to withdraw from entrepreneurship. The completely standardized direct effect is visualized on the right. This partial scatter plot is generated in exactly the same way, but doing all those computations using residuals from regressions with standardized variables. The slope of the line here is minus 0.088, and it's the completely standardized direct effect. Two entrepreneurs who differ by 1 standard deviation in stress, but with the same business-related depressed affect, are estimated to differ by 0.088 standard deviations in withdrawal intentions, with the more stressed entrepreneur feeling lower intentions to withdraw from entrepreneurship. Okay, now here is what we've been working toward. The whole point of this example has been to show that I wasn't lying to you earlier when I said the total effect of X breaks up into a direct effect and an indirect effect. Remember, C equals C prime plus the product of A and B. Here is everything together using the unstandardized or raw effects. Our indirect effect is the product of A and B, 0.173 times 0.769 equals 0.133. So we can say that two entrepreneurs who differ by 1 unit in their economic stress are estimated to differ by 0.133 units in their withdrawal intentions, with the more depressed entrepreneur being higher in withdrawal intentions. We can say higher because the indirect effect is positive. But remember, we have to interpret the sign in light of the signs of the components, A and B. The indirect effect is positive because A and B are both positive, meaning that the greater stress seems to prompt more business-related depression, which in turn leads to greater withdrawal intentions. Now, leads is one of those loaded terms, right? It implies cause. But this is a mediation model, and mediation is a causal process. I'm assuming cause-effect here, and in the direction I've modeled it. I may be wrong about this, though. We'll talk a little bit about that later. Now notice that our total effect of economic stress on withdrawal intentions, 0.056, is equal to the direct effect of economic stress, minus 0.077, plus the indirect effect of economic stress through depressed affect, or 0.133. Add those up and you get 0.056. So it worked, just like I said. Now, I recognize that one example doesn't constitute a formal proof, but I'll tell you this will work for any data you use so long as you're estimating your mediator and your outcome using OLS regression analysis. At the top of this slide, I've given you the interpretation of all the effects we've estimated in a generic form. They apply regardless of content or context. In the bottom, I've given you a more specific interpretation that considers the substantive meaning of these effects. We've essentially gone over all this already. You can read the specific interpretation at your leisure, but I did want to bring to your attention the direct effect here. Remember, we have two processes at work. The indirect effect seems to prompt greater withdrawal intentions through the economic stress prompts greater withdrawal intentions by elevating depressed affect. But there's another pathway that seems to be reducing withdrawal intentions as a result of economic stress. Whatever that process is, it's not operating through depressed affect. We take those two processes, the differences in withdrawal intentions between entrepreneurs who differ by 1 unit in stress, the different operating directly as well as indirectly, and they add up to produce that overall total effect. This is an interesting circumstance here in which our total effect, notice, is smaller than both the indirect effect and the direct effect. That's not very uncommon. And it's a further illustration of how we shouldn't be relying too much on the total effect to decide whether we should do a mediation analysis. The total effect could actually be the smallest of the effects. When you break the total effect up into its pathways of influence, those pathways could be even larger than the total effect, as they are here, if you consider larger, ignoring the sign of the effect. I said that this path analysis algebra that breaks a total effect into direct and indirect components works for the completely standardized metric as well. So here it is. Our completely standardized indirect effect is the product of completely standardized A and completely standardized B. So 0.340 multiplied by 0.446 is 0.152. So we can say that two entrepreneurs who differ by 1 standard deviation in their economic stress are estimated to differ by 0.152 standard deviations in withdrawal intentions, with the more stressed entrepreneur being higher in withdrawal intentions. We know already that this positive indirect effect results from a positive A and a positive B. So this 0.152 unit difference in withdrawal intention attributable to this mechanism is the result of economic stress prompting greater negative affect, which in turn results in greater withdrawal intentions. And notice that, as I promised, our completely standardized total effect, 0.064, is the sum of the completely standardized direct effect and the completely standardized indirect effect. Those add up. So here's our generic interpretation of all of the completely standardized effects. I largely have gone through this already. And here's our specific interpretation. And it essentially says that our 0.064 unit standard deviation difference in withdrawal intentions between entrepreneurs that differ by 1 unit in economic stress breaks up into a 0.152 unit difference resulting from this mechanism, this indirect process, and then a 0.088 standard deviation difference, but downward, resulting from the direct process, the process that bypasses depressed affect.